This is a short video that aims to recap what we've been talking about with the existence of primitive elements in the unit groups mod_n. In particular, so far, what do we know? From the previous videos, we saw that the two types of unit groups that have a primitive element we see are the following: z mod p z star, where p is just prime, or something like z mod p to the n z star, where p is an odd prime. So in particular, whenever p to the n is an odd prime power. So anytime p is not 2. So in those two cases, those two unit groups are guaranteed to have a primitive element. And for us, remember, that meant that you had an element of order phi of n, or in our case 5p, or 5p to the n. But those happen to also be the size of each of these two groups themselves. That means that they're cyclic. If you have an element whose order is the same as the order of the group, then you have a cyclic group. So these are the two cases that I know that I have cyclic groups from like an abstract algebra point of view. There are more cases instead of just pz and p to the nz, in which case you also get a cyclic group, and hence a primitive element exists. But those are a little bit beyond what the book needs. So, but if you look at, like, say, any abstract algebra book, it's pretty typical that they'll map out all the possible cases. If you're interested in that, go check it out. So what I'm going to do is just go through a couple examples of just demonstrating some of these, and then also some weirdness. What I'll also do, just because it's convenient for me for like presentation, you can convert this to this IPYNB. It converts everything that I'm doing into like kind of like a Jupyter notebook, and so you don't have to worry about this. But if you are interested in that kind of stuff for like presentation purposes, I think it should make life a little bit easier. But let me see. I want that to be like its own block of code. Cool. So now I can kind of consider these each separately. So let me talk through what's going on in each of these. So in the first example here, I've got that I'm going to talk about the integers mod 49, and in the next one, r underscore units is what's going to be, so this is z mod 49z star. So that's the group of units. So I'm just calling it r units. So the next thing is I want to know what's the order of this group. And so I'm asking Sage in this line right here, right where? How about right here? Oops, right there. To just go ahead and tell me what is Euler 549. What is 549? So like how many numbers are relatively prime to 49 up to 49? It should be 42. And you see in the next line, I use that. So right here. So I'm going to talk about what are the divisors of phi of 49. So you see I'm going to list out what are the numbers that divide 40. In this case, it's 42. Notice in that range function, I got 42 plus 1, just because that range function in Sage doesn't include the right endpoint. In the condition there, if 42% sine y equals 0, that's trying to say the remainder, when you divide 42 by y, is equal to 0. In other words, y divides 42. So I just want to make a list of the divisors. In the next line, right here, I go ahead and just tell Sage, okay, tell us what the divisors are. And then now, I'm going to... This line really right here serves as like a header for two columns. I'm going to have one column that are what are the divisors of 42, which is 549, by the way. And then you see that /t, that's like some kind of a tab character in Sage, and that's going to make stuff like an alignment kind of pretty. So in the next column, that's the header, elements of order d. And now in this next line, I just made a little for loop. So like for d in my list of divisors of 42, I'm going to do the following. I'm going to print what d is. So in the first column, it's going to be all the divisors printed. And then you see I did these /t. That's just going to make extra space to the second column. And then you see that the second column is going to be the following list. It looks like any x for x and r units. So we're just going to go through the elements of z mod 49z star. And what I want is, I just want you to list out what are the elements that have order d. And so that's the if x dot multiplicative order blah 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 is equal to d. So if I run all this code here, cool. So from the beginning, any of the print statements, it tells me that the order of z mod 49z star is 42. The divisors of 42 are 1, 2, 3, 6, 7, 14, 21, and 42. And then you see the last thing is my two columns. I'm going to list out the divisors again, just in that first column. And then I'm going to go through each element of z mod 49z star, and I'm going to tell you how you should read this is 48 has order 2. 18 and 30, they both have order 3. Scrolling down the list, I see that it looks like there are something like 12 elements in the bottom that have order 42. So z mod 49z, star, it's a nice group, right? Because 49 is 7 squared, that's an odd prime. You expected a primitive element to exist from the theory, and we just demonstrated that, yeah, there's 12 primitive elements. There are 12 elements here that have order 42, which is, again, 549. So what's maybe a more badly behaved example, and this is on a homework problem for homework 3, which was to take a look at Z mod 36 and look at the units mod 36. So the first thing you might notice is that 36 is not prime, and it's not a prime power, an odd prime power either. So that kind of makes us think we're going to expect some weirdness. There's the potential for weirdness. So let's go ahead and make the units mod 36. So again, that's what this little thing does here. Maybe there are other ways to do that. This is just convenient for me. So this is Z mod 36 Z star. And let's see what else. Then I'm going to go ahead and figure out what is 536. In other words, what's the order of this group? And it should be 12. So that is just reading off what that line is. I'm going to do the same kind of thing where I want to list out what are the divisors of 12. And I guess I probably didn't need to go all the way up to 36. I probably could have just done 12. I think that was a typo on my part. I suppose that I could probably fix it now. Let's just do 12. I just want to list what are the divisors. So again, I'm just looking the numbers 1 through 12 and seeing which one gives me a remainder of 0 when I divide. That's what that line does. Same kind of thing. I just want Sage right here to tell me what are the divisors and just go ahead and list them. And then now I'm going to, again, make like the tab character here. I'm going to make 2 columns. The first column are going to be what are the divisors of 12, and the second column is going to be what are the elements of order D, where D is a divisor of 12. And then now, just as above, I'm going to fill in what the columns are with this 4D in divisors here. I'm going to print the following. So for each D in divisors, tell me what D is, do a little alignment here, tab a few spaces over, and then it's this similar X, so build this list here. So look through the elements of Z mod 36 Z star, and I want you to list the ones that have order D. So that should list the elements of order D from Z mod 36 Z star. So if I try to run this block, let's see what it gives me. All right, so the order of Z mod 36 Z star is 12. The divisors of 12 are 1, 2, 3, 4, 6, and 12. And then now when I look at my 2 columns here, the left column is just listing the divisors again, and in the right column, we're just searching through this group to find an element of order D. So you see that like 17, 19, and 35 each have order 2. Now here's the weirdness. Like 4 is a perfectly good divisor of 12, but there's no element in this group of order 4. That's some of the weirdness we expect, because 36, it's kind of a bad composite. It's not just a single odd prime power. Similarly, there's no element of order 12. So since 12 is the order of the group, and there is no element of order 12, this group can't be cyclic. And then moreover, in our special case here, remember that a primitive root has order 5n, in which case is 12, so there's no primitive roots for this group either.